This video is going to be pretty different from most of the videos that I do in my code-based series because after I started recording this, things just started turning out in a much different way than I expected, and it has turned into a lot more than what one video normally contains. It wasn't originally on my to-do list to look at color correction and linear color space versus sRGB types of concerns, but when someone mentioned that that would be an important part of getting the anti-aliasing right in a YouTube comment, it did pique my interest. And then I did this little jam project in order to make the audio visualizer for the podcasts, and while I was working on that, I decided to dabble with the color space stuff. So, since I had already done it and someone had suggested that I look at it, I figured it wouldn't be too big of a deal to drop it into the ongoing experiments with anti-aliasing and see what happens. The easy thing I could say here is that I didn't really like the results. After looking at the various anti-aliasing methods I've got, the velocity and non-velocity variations, and the sign distance versus pixel coverage variations, I just felt like everything looked better when I wasn't doing color correction in the anti-aliasing. But the comment that I had originally gotten that suggested this told me that it should look better when I do anti-aliasing, or it should be more correct when I do anti-aliasing with a linear space color blend. From there, I went and did a lot more reading as much as I could on different anti-aliasing techniques, getting into really specific stuff that I had never heard of before, which was super interesting. And I did a lot of thinking about this on my own and sort of piecing together the way the theoretical building blocks make sense together. And I just can't shake this feeling that it really only makes sense to expect linear color spaces to be the right way to blend colors when you're doing anti-aliasing. Despite that, things just looked better to me when the colors for anti-aliasing were blending in sRGB space. So I have a few goals for this video. The first is to explain the theories of color conversions and anti-aliasing as I understand them. Along the way, I'll attempt to clear up some terminology confusion. It might just be a matter of different people using the same word in different ways, but I think there are some ways that these terms are getting used without people realizing that they have different meanings, and that is causing some issues when I try to talk to people and ask questions about this topic. Then I'll spend some time presenting some experiments. I'll show the setup for the experiments and the results that I'm getting, and then relate those to how they validate or challenge the theories that I'm talking about. In particular, the challenge that it's going to pose at the end is if it does indeed look wrong, even though it correctly matches the theory, then that means the theory is wrong in some way, and if it doesn't look wrong, then it means I found a bug. Either way, I will have either made progress on showing that there's something wrong with the theory as I understand it, and then clearing up the questions that I'm trying to ask, or in rooting out the bug that's making my shapes not look the way I want them to look. And to wrap up, I'll go through some ideas and suggestions about what might make all of this work, and see if any of it solves the problem, and if not, pinpoint why it isn't working. Before I get into too many of the details, I want to give a special thanks to all the people who put a lot of work into helping me understand different parts of this. First of all, there was Martins on the Discord over at Handmade Network. He spent a lot of time going over how I was using opengl. Although it turned out that there was no bug to find in my opengl code, having an extra pair of eyes on that did help me to rule out the possibility that that was the issue, which is much appreciated, and it gives me a little bit more confidence so that when I'm explaining to you how I interpret the opengl APIs, that I'm not giving you wrong information. Second, a person who goes by Lu Chong on Discord and on Twitch helped me during my Twitch streams for the podcast audio visualizer by pointing me in the direction of some stuff that really helped me understand more deeply the issues with sRGB and linear color space conversions, and in particular, some of the mistaken assumptions people make about how things should look given one path or another. And so all of that stuff really helped me clear up and clarify some things that I think I hadn't fully appreciated before, and I'm going to try to include some of that insight in this video as I'm going over the theory. So big thanks to Lu Chong for pointing that stuff out. And then finally, a big thanks to Miles on the Handmade Network forum. He wrote a post that had a bunch of thoughts about what might be going wrong, besides just the code being wrong or the theory being wrong, but sort of the other incidental variables that I might be accidentally ignoring. And if you watch to the end, you'll see that actually one of his suggestions does in fact solve the problem, and I only now know that because I'm recording these thank yous to insert here at the beginning, but most of this video was recorded along the way before I had some of that helpful information, and so I didn't end up testing that until quite near the end of the process. But I think that the journey is quite worth it, and I'm grateful to Miles for pointing me towards something that actually let me solve the problem. Chapter 1. Theory for sRGB colors. The key point to this whole conversation is that the human eye does not respond to light brightness in a linear way. To be more specific about what that means, if I have a spectrum of lights, each at a different physical brightness, where by physical brightness we mean some kind of measurement of the amount of energy coming from the light, the number of photons coming from the light, the luminosity of the light, any of these kinds of quantities are measuring the physical brightness of that light. It will turn out that when I spread those lights out on a spectrum from most to least bright or from least to most bright in front of any human, their eye will not interpret that as a steadily increasing amount of brightness. Instead, it will seem to be dark on one end and very rapidly get bright and stay bright for a large portion of the gradient. For the purposes of this discussion, we don't need to go any further into the color theory part. There's a lot of interesting stuff to be said about rods and cones in the human eye and gamut and the color range and what colors can be represented on a screen. None of that is really relevant to what I'm talking about now. The only detail that we do need to spend some time understanding is how to calculate the human eye's response given a brightness value. Now, we don't need to do that literally with literal units. What we need to be able to do is how to interpret that in relative terms. So if I increase the brightness by doubling it, what is that going to do to the human eye's response? Roughly speaking, that function can be approximated by a function of x to the 1 over 2.2. So what that means is that if I have some light source with some known brightness and I double the brightness, the human eye will perceive about 2 to the power of 1 over 2.2 or a 1.37x increase in perceptual brightness. Again, this is a gross oversimplification of how human light perception really works, but this is the theory that we are working with when we talk about something simple like sRGB linear conversions. Now, this fact about the human eye is going to turn out to be important twice in our understanding of sRGB linear conversions, not just once. Since we know that the human eye is more sensitive to small variations in dark light sources and is not very sensitive to small variations in very bright light sources, it doesn't make sense to allocate our precious resource of bits or information equally across the domain of light or the spectrum of light in accordance with the physical brightness of things. Being able to tell the difference between two slightly different dark things is a useful thing a human can do, and if a human can't tell the difference between two equally distant, very bright things, why should we make devices that can display those imperceptible differences? Instead, what we choose to do is to use our information efficiently by mapping the values of input colors to brightness on a curve that puts more values on the dark side and less values on the bright side. Or to put it another way, we invert the human eye's curve when we go to display something so that equal changes in the input brightness will have perceptually equal values in the output brightness rather than physically equal changes in the output brightness. Now, don't worry if that idea was a little hard to follow. We're going to get more explicit and have some practice with how to apply this theory next. What we end up with after exploiting this idea in both our hardware and software is that we have two different color spaces. By color space, what we mean is a way to encode the concept of a color as a combination of numbers, right? So a color is not actually a number. In reality, it is something different. It is a physical property of the world, and we create the effect of that color through a device. But we also want to encode the concept of that color into the software, and the ability to do both is what allows us to program something like a display with software. So on one end, we want software to be able to create data that matches what the device is expecting in such a way that it can display what we want it to display to a user. But we also want to be able to use the color values that we're pushing through our software to do computations. And so there are two different ways to encode the concept of a color. One is in the way that matches what hardware can display, and the other is in the one that matches the actual physical reality of how much energy or how much intensity or how much brightness there is in a particular color. These two different ways to encode a concept of a color into a triplet of numbers are the two different color spaces. And we don't want to mix and match when we're using one or the other. Some routines will be written for one color space and other routines will be written for another color space. We can think about this as extended type information, if you'd like. The sRGB color space is the one that our monitors actually use if we're using standard computer monitors, and it's also the encoding that is used to save things like bitmap images and PNGs, unless you are manually doing something different and you are intentionally encoding your image in a linear space or some other space, then it is being encoded in sRGB. When you go onto the web or into Paint or anything like that, and you type in the hex value for a color, you are telling the computer to take your hex value and assume that it was encoded in the sRGB color space and use that to start creating some colors or some painting or to color the background of your website or whatever the case might be. On the other hand, if you look up an algorithm to convert RGB to HSV or HSL, or if you are going to blend two colors together to make a gradient or to create a transparent overlay, the appropriate way to do this, if you want the blend to not darken the results when there's a certain amount of contrast between the brightness or the colors, is to use linear combinations of colors represented in the linear color space. In other words, the reason we call the linear color space linear is because it is possible to take linear combinations of colors that are encoded that way simply by adding the numbers together. Now, not all programs actually do all the work of converting out from sRGB into linear before they start doing color manipulations. They might blend colors together or create gradients in the sRGB color space either intentionally or because they are what we call gamma naive. Gamma because that's the name of the variable that controls that curve. If you recall, I said that a rough approximation of the human eye's response to light is x to the 1 over 2.2. Well, in that equation, we can call the 2.2 gamma. Gamma is the name that is often given to that particular parameter in this sort of conversation. Another name for all of this is gamma correction. And a gamma naive application is one that basically pretends like there is no such thing as an sRGB space or a linear space. It assumes its input colors can be added together, that they are linear combinations of colors derived from images and from user inputs are perfectly valid, and then puts those linear combinations into the output with no conversion into or out of the linear color space. On the other hand, a gamma-aware program would be one that knows which of its inputs are encoded in sRGB space, knows which of its outputs need to be encoded in sRGB space, and knows that it cannot use any values that are in sRGB space to go through linear combinations unless that is creating a very specific sort of effect that it knows it wants to create. It generally will first take all of its inputs that are known to be in the sRGB space and run them through an sRGB to linear conversion. And then, after it's done all of the color manipulation it needs to do by adding and combining colors together, it will create a final image by taking the outputs that are currently encoded in a linear space and convert them back to an sRGB space for display to the monitor or for saving to a file. Now, this is where we can get some practice with using this theory. What we're going to want to do is be able to predict when running a conversion is going to make our numbers bigger or smaller so that we can visually inspect if the results we're getting along the way make sense. And we also want to make sure we don't get ourselves tied up in knots and confused. We want to remember that the idea here is that when we convert from one color space to the other, we are actually keeping the color the same. We are representing the same color through the conversion. It's just that we're changing which space we're using to encode the concept of that color. If we start thinking to ourselves that running linear to sRGB brightens things, or that running sRGB to linear brightens things, then we're thinking the wrong way. It's changing the numbers never brightens or darkens things. What brightens and darkens things is not using the color spaces appropriately in such a way that the numbers turn out larger or smaller than they're supposed to at the end of the pipeline. The conversion function for sRGB to linear can be roughly modeled by the simple function f of x equals x to the 2.2. So what this is going to do, since all of the inputs are considered to be in the range from 0 to 1, and all of the outputs are considered to be in the range from 0 to 1, is it's going to fix the values 0 and 1. When we put a 0 into the converter, it's still going to put a 0 out, and when we put a 1 into the converter, it's still going to put a 1 out. But in all the values between 0 and 1, it's going to decrease the size of the value. For instance, if I've put 1/2 into the converter, then I raise 1/2 to the power of 2.2, I get 0.218 approximately. Again, remember, that's the effect that it has on the number that I put into the function, but in concept, if everything is working correctly, the color described remains the same. It's just that in the input side of that function, the color was described in sRGB, where 0.5 encodes a particular kind of gray, and after putting it through that function, the number is now 0.218 in the linear space, which encodes the same gray. Next, we can consider what the other end of the pipeline does when we go from linear to sRGB. And one property of the system should be that if I don't do any blending at all, and I run both converters, I should end up right where I start, right? It should be possible to reconstruct an image by first linearizing it, taking it from the sRGB to linear space, doing nothing to it, and then taking it from linear back to sRGB. We're trying to hold colors constant in concept, so if I've converted it from one space to another and back and held the color constant all the way through, I should end up with the same numbers that I put into it. And so this has to be the inverse function, f of x equals x to the 1 over 2.2. So for instance, if I took 0.218, the middle gray that we got from the sRGB to linear conversion earlier, and then I convert it back using linear to sRGB via 0.218 to the power of 1 over 2.2, I should get back to 0.5, and I do. So to summarize, a sRGB to linear conversion makes the numbers smaller or keeps 0 and 1 fixed, and the linear back to sRGB conversion keeps, again, 0 and 1 fixed and makes all the rest of the numbers bigger again. This can be a handy tool for sanity checking some results. For instance, if I have an image coming out way too bright, I can think to myself, which conversion makes numbers bigger and which conversion makes numbers smaller? The one that makes numbers smaller is sRGB to linear, so possibly I forgot to run that at the beginning. Maybe I'm running linear to sRGB, but my input colors are still in sRGB, so what I'm in effect doing is making the numbers even bigger even though they were already in the sRGB space. Or maybe what's happening is I am doing an sRGB to linear conversion, but then my pipeline accidentally does linear to sRGB twice. On the other hand, if I'm getting images which are way too dark on the output, then what might be happening there is that I'm doing an sRGB to linear on the input side of the pipeline, but never actually doing a linear to sRGB on the out side of the pipeline. Now, there's a pretty good opportunity to get confused here, because earlier I said that these functions don't change the color, they just change which space it's encoded in. And that's true if everything matches up. But these functions definitely don't preserve their numbers. So if I don't have everything matching up, for instance, if I think I'm getting a linear color input and converting it to sRGB, but I'm actually already getting a color that's in sRGB, I'll have no way to know that. Either way, it's a triplet of numbers. And so the function will modify those numbers. And as soon as there's a mismatch in those color space types, the input into a function is not the color space that's expected, I'm going to start getting wrong results. So watch out for that. We don't want to get confused. These functions in concept hold a particular color constant, but they don't hold the numbers constant. So when we have a bug, the bug will be because we failed to match up the color spaces at one level of concept, and it will be at another level of concept because the numbers are getting modified too big or too small. Chapter 2. Clearing up some sources of confusion around sRGB, linearity, opengl, and more. I have here two gradients, one on the left side and one on the right side. They both start from white and go to black, but they are not exactly equal in appearance. They do look different. Now I want to ask you which one of these gradients appears to increase in brightness at the same rate all the way across the gradient. One of them should look like it's a steady increase in brightness all the way across the gradient. Just take a moment and think to yourself, which one looks like that one? Now, what would you be thinking if instead I asked this question? Which one of these gradients is linear? In my experience talking about this with several people, some people are interpreting the second question as exactly the same as the first question. To them, to ask which gradient is linear means to ask which one appears to increase in brightness at a steady rate. But other people interpret the question which one is linear as asking which one of these increases in brightness at a physical level at a steady rate. And yet others assume that it means which one of these is encoded in the linear color space. And yet others might assume that it simply means which one of these is actually a linear increase in numbers that are encoding the brightness in the final image encoding. The point of this is to highlight that this word linear is highly overloaded in this particular space. It has a very important meaning in its description of the linear color space because linearity means the ability to make linear combinations of things. And so when we talk about the linear color space, what we mean is that it's a way of encoding colors that also has the ability to blend colors in a physically accurate way simply by making linear combinations. If you recall back in chapter 1, I said that the human eye's response to light was going to come into play not once but twice in our understanding of all of this. The first time was in motivating the idea of sRGB and its implementation into hardware. Now it's coming back again to inform us about what we should expect to see when we create different kinds of effects and how a human will actually perceive that. In order to show you what I'm talking about, it's time to switch over to building some of the setup I'm going to use to run the experiments through this video. Here I'm setting up the experiments program. It's going to be a separate standalone program in its own repo that I'm going to post along with this video as soon as the video comes out, so that anyone should be able to get it, build it, and run it if they have the ability to build and run a C file on a Windows operating system computer. I'm piecing this together out of the Scratch OpenGL program and the example OpenGL program that I already have in my codebase. So it does take about an hour and a half or so, but it's not too bad to get everything up and running here. And once I fix the couple of bugs that always happen the first time you set up another OpenGL program, I go and set up the main setup for this experiment, which is going to be a black full screen window with a divider down the middle. On the left side, I'm going to show you what a gamma naive rendering of something looks like, and then I'm going to run the exact same rendering process through a different pipeline that will do gamma correction on the input to the colors and on the output to the colors. And so I'll be able to put each one up side by side and walk through the different experiments that I'm going to show throughout the whole video by adding them to this experiment program. And then at the end, you can go and look for yourself and see it without any video compression artifacts, possibly making you unsure about what I'm saying or if what I'm saying is true. Okay, so let's get to the end of this programming session here and look at the first experiment. My first experiment was to add a gradient. I put this at the very top of the window on each side of the divide, and this will get us back to the question I was asking earlier about what does it mean when you say a linear gradient. If you think a linear gradient is a phrase that refers to a gradient that appears linear to your eye, then I think most people would agree that this one on the left appears linear to the eye. It feels like it goes from fully bright to a middling gray to a dark, fully black on the other end in a gradual way that is steady across the entire gradient, whereas this gradient on the right-hand side does not appear to go linearly in that sense. It appears to be fairly bright for a while and then fall off rapidly towards the edge. Similarly, if you were to define a linear gradient as one where the numbers in the image itself are increasing at a fixed rate as you walk along the image in the direction of the gradient, then this would also be considered a linear gradient. That's the same thing, because when we are encoding something in sRGB, linear changes to the brightness values result in linear changes to the perceptual brightness that we end up seeing. On the other hand, if you think that a linear gradient is a phrase that should refer to the idea of a gradient that is rendered evenly in the linear color space, then the one on the right is a linear gradient. In this gradient, the actual energy given off by each pixel, or the amount of photons or the luminosity of each pixel, is falling off in an equal amount in a linear way across the screen from left to right. So the point of all this, again, is to emphasize that the phrase linear can get very confusing. I think that it's appropriate to use the term linear color space for the color space in which linear combinations of the numerical representation of a color corresponds to physically accurate blending of light, but I don't think that any other use of the phrase linear or word linear should really be allowed. I think it leads to too much confusion. At the very least, it's better if we qualify it. So we will call the thing on the left a perceptually linear gradient from now on, at least in this video, and the thing on the right, I will call that a physically linear gradient for the rest of this video. Now, you might have some doubt that I've implemented this correctly. So in a minute, I'm going to go through in detail how the OpenGL sRGB stuff works and how this implementation works so that you can see that I'm probably not doing anything wrong. But just in case even looking at the code doesn't convince you that I've done the sRGB conversions correctly, there is another way we can test this, which is I'm going to add a second experiment below the first one where I grab the extreme values and the middle value. And that way you can see just what the center value looks like and compare that to what it looks like on the gradient. And you can see there quite clearly that the middle gray on the right-hand side, on the sRGB corrected side, is a little brighter, which is what we said we theoretically expected. And the boxes on the left show a middle gray that does appear to be more perceptually in between white and black. So if you had any doubt about how the gradient was being interpolated by OpenGL or by my own code, this clears that up because now there's no gradient. We're looking at exactly what middle gray would look like. On the left, we're seeing what 0.5 as a rectangle looks like when there's no color correction applied afterwards. And then when I start with the same number, 0.5, and put it through a linear to sRGB, it does get brighter. While that does help to rule out the possibility that there's some weird curve being applied by the interpolation of the colors that is not shown obviously on either the code I've shown you or in the OpenGL spec, what it doesn't do is maybe convince everyone that the gradient on the left, the one that is not going through any color correction, really corresponds to putting down decreasing values starting from 255 and going all the way down to 0. But to look at that, we can make a non-visual part of the test that will read from the back buffer after we've rendered to it and directly test that all of the values relate to each other in the way that they should by an assert. If I can run my program without it crashing, then that will confirm that the values in the buffer start at 255 and decrease one at a time all the way down to 0. The point of all of this is to be able to finally say that we can't ignore the way the human eye responds to light when we're trying to create certain effects. If we want something that looks perceptually linear, then doing a linear numerical fall off in the sRGB space actually has that effect. It's very easy to get confused here and think that what should happen is that you need to do color correction first in order to get the effect of linear fall off. After all, the sRGB monitor is applying some kind of curve to the values that are coming in, so shouldn't it make a non-linear looking gradient? But that's forgetting that the way the human eye responds to physical quantities of light already has a curve built in. If you make a gradient that is got physically linear light fall off, then it's not going to appear to have perceptual brightness fall off that is linear. So this is the second time that fact about the human eye is showing up, and we have to remember it's not just an inspiration for how the hardware works, it's an actual physical fact that when we start using physical light to compute what happens in our image processing instead of sRGB values, we're going to get effects that correspond to what happens when physical light behaves according to whatever curves we put into our, analytics and our geometry and so on and so on. So a gradient that is physically linear is not going to appear linear because of that fact. And it's important not to forget that it's going to show up again on this end of the pipeline, and it's not just a part of the setup. Now, another reason all of this can get very confusing is because of the naming scheme that OpenGL uses to actually control all of the linear to sRGB conversion functions that it supports. Now, this problem might be better solved in other APIs that maybe are designed better. I don't know. I'm not reviewing those. And I don't know them well enough to go over them. But I know that anyone like myself who went through the OpenGL path to learning graphics programming will probably have hit this stumbling block before and had to recover from it. So the first thing is to remember that what matters here is nothing but when we plug in a conversion function. There is no way to tell the difference between a triplet of numbers that is sRGB and a triplet of numbers that is linear color. They both just look like three numbers. If it's in floating points, then it looks like three numbers between 0 and 1. sRGB is not like more clamped than linear light or anything like that. And of course, if it's in a byte encoding, so maybe we've got a byte for each channel, then the sRGB is going to more efficiently cover the space, but we could make a linear representation of color that way too. It would just have a lot of redundant values that are so slightly different that we can't really see the difference with our human eyes super well. Those would be the bright values. They would look too similar for us to tell the difference between them. But nevertheless, you could think of a byte version of linear colors as well. The point of all that is to really drive home this idea that a triplet of numbers, no matter how it's encoded, is not really going to tell you if it's sRGB or linear. They're going to look the same. So the only way to get the whole system working right is to know when values are supposed to be sRGB and when they're supposed to be linear. In the sort of same way that a type system makes sure that 4 bytes are treated like an unsigned integer or a signed integer or a 4-byte floating point number at appropriate times and doesn't get confused and start treating what used to be an integer as a float without first providing a conversion path, right? That's the point of a type system. And in the same way, we want to think about our colors as having this extra kind of type information. Yes, it's made up of triplets of numbers, but it also has to be encoded in one of these spaces. And if we don't know which space a particular triplet is encoded in, there's not really anything we can do about correcting that. So we always have to be keeping track of it. So in OpenGL, the problem is instead of actually exposing functions that do the conversions, what they expose are types, basically objects that you can create, an sRGB texture or a frame buffer with an sRGB texture attached. And so this puts the types into the system as if types really were real, and they aren't quite actually real. So when you go to actually write the code, you want to think about when you are and aren't applying the conversion, but the way you control whether you are or aren't applying the conversion is by setting up the texture to either have the linear type on one side and the sRGB texture on the other side, or vice versa. And by getting the type markers set up correctly, OpenGL infers whether or not to run this extra function for you. So in OpenGL, when you want to take a texture and convert it from sRGB to linear, what you have to do is upload your texture data to an sRGB formatted texture. If you put it in an RGB formatted texture, that is a signal to OpenGL that when it pulls colors out of that texture, it should assume they're already linear. But if it is an sRGB texture, then when it pulls colors out of them, it's going to assume it first needs to do an sRGB to linear conversion. You get that? So it's not the case that you get to call a function that says sample and convert. You just call sample one way or the other, and it's whether or not you put this extra type marker on your texture, and whether it's RGB or sRGB, automatically tells OpenGL whether or not to run the function. On the other end, when you're rendering out to a window or to a frame buffer with a texture attached to a color slot, if that texture attached, or if the frame buffer itself is an sRGB texture, then if you also have the frame buffer sRGB feature enabled, then those two facts together means that it will convert the final output color to sRGB. Now this can be confusing, and we're going to look at some more of it in detail in a minute here, but again, the main idea here is that when the end point, when the outgoing texture, when the texture that's being written to is labeled as sRGB, then whatever color comes out of the shader is assumed to be in linear and then is converted automatically to an sRGB format. So you'll notice that according to this model, an sRGB color never goes through the shader. The shader is considered to always be getting linear colors in, because once the sampler returns, you already have a linear color. The conversion happened behind that sample call. And when colors go out, they're still linear, and the conversion into sRGB happens automatically in the part of the pipeline you don't program in the shader. Now that might not sound like a big deal. It doesn't sound like too hard of a problem to manage, but it leads to confusion, and here's how. When you don't touch sRGB features in OpenGL at all, what you're in effect saying is that everything you do is linear. Your inputs are linear and your outputs are linear according to the lingo of the API. You're saying my texture is RGB, my frame buffer is RGB, I haven't enabled inputs or output conversions, so you're thinking about it like it's all linear. But that's actually a lie. Even though you never write a single feature that deals with sRGB, it's still going to be true that all of your input textures are encoded in the sRGB space, and that all of the output colors are expected to be encoded in the sRGB space by the monitor. So what's actually happening is, even though you never wrote sRGB, the entire program is doing color math in the sRGB space. Now, this is where it gets even more confusing. We said a minute ago that according to the mental model OpenGL gives, linear colors are the only kinds of colors that go through shaders. But this stops being true in a gamma naive program, because since no conversion is ever happening, the colors are coming in encoded in the sRGB space, they're going out encoded in the sRGB space, which means they are actually flowing through the shader in sRGB space, and OpenGL is sort of just doesn't know. So this is where it gets confusing. The fact is that even though they didn't put it in the API, there was always sRGB colors there, and then the sRGB features allow you to deal with sRGB, but what they actually give you is the ability to convert from sRGB to linear and from linear to sRGB. If you don't use the sRGB features, then you are always in the sRGB space, which is kind of weird. Now, whatever API you're using, the transition from a gamma naive version of your program to a gamma aware version of your program basically just means taking everything that you already wrote that was in linear space, all of your shaders, all of your color math, and switching it all into the linear space. That's the basic way of thinking about it. And all you have to do to make that happen is to take all of the input colors, and the first time you touch an input, before you do anything else with it, you process it once to do a sRGB to linear, and then at the very end, last possible minute, you take the output colors you're about to send to the frame buffer, and you do a final linear back to sRGB conversion on that end. So you take the program you already have with all the data flowing through it, and you just kind of sandwich these conversions into the beginning and end. It's a new bookend that happens in the pipeline. Now that sounds easy enough, but you do want to watch out for one other way that this can get you. Because, for instance, in OpenGL, when you're talking about input colors, you're talking about the textures that you're sampling, but you're also talking about the uniforms and vertex attributes that contain colors encoded into numbers, right? I might have a uniform that says what I want a particular batch of quads to be shaded as a particular color, or I might have each vertex shaded with a particular color or something like that. And if I'm encoding those colors in my first program in the sRGB space, and then I decide to go gamma aware and I start doing linear conversions in and linear back to sRGB conversions out, I might forget all of those other colors that are not coming in through textures, but are still input colors to the color math that is happening. So you got to watch out for that. And I want to run a quick experiment to see that in action, because while it's possible to kind of account for that, it's a little bit tricky, and I want to see up close exactly how bad that trickiness is. So this is an experiment not to demonstrate something that I already am pretty sure I know, but actually to answer a question that I have, which is, if I do the recommended easy fix for my input colors when I have them encoded in sRGB in, say, a vertex attribute, and I want to convert them to, say, the linear color space before I start using them in the rest of the shader, then what I generally would do is just raise it to a particular power to run the sRGB to linear conversion. But from my understanding, that raising it to a power isn't quite accurate. The sRGB space is a little bit more complex than that. It's a slightly piecewise function with a little bit of linearity in the small values. And if that's true, then I should be able to detect that by comparing the results of doing the naive sRGB conversion to the correct sRGB conversion that is run by the texture sampler. So I want to see that just to confirm that that part of my understanding is correct. All right, what I did in this experiment was make a modified version of my basic shader that still takes a color from the vertex data, but then runs it through the simplified sRGB to linear conversion, where I just take each RGB channel and put it through the function f of x equals x to the power of 2.2. That's the simplified sRGB to linear conversion. And then I took another shader, and this one was just a texture mapping shader, and I sent a shader through that, or a texture through that had intensity values that match the rectangle colors that I was attaching to the vertexes for the other case. So on top here, we can see what the texture looks like when it's getting mapped, and on bottom we can see what it looks like when I take colors from vertex attributes and pass them through that approximate x to the 2.2 function. I can clearly see here that the small values, the darkest values, don't actually match. And then as you go up about a quarter or a third of the way into the bright values, they sort of sync up and then they match pretty well after that. So it's a good approximation for most of the range, but there are a few colors in the dark part of the spectrum where the simplified conversion is making colors come out darker than the correct conversion. So let's see if we can go track down the exact formula and implement that and get a better match to what the texture sampler is doing. After looking at a couple of sources that all sort of agreed on the basics, I found this web page and I really liked the way it was laid out. So I follow what it has to say, and I'm able to write a shader that does in fact show I can match the texture sampler's results by using this conversion formula. Chapter 3: Non-gray colors in linear color space. So far, I haven't mixed in anti-aliasing, and I've only been talking about the way color correction affects the brightness, assuming all pixels are going to be some shade of gray or white or black. But a big reason to actually do color correction is because it correctly handles blending of colors that aren't just gray. We haven't looked at that at all. Another good reason that I have for looking at this first is that without this, I've really only built a pile of reasons to not do linear color space conversions. Since I probably want my gradients in my system to be perceptually linear, and it's easier to get that effect if I don't do linear color space conversions, it's not clear why I would do this, but I think it will become more clear when I look at what happens with gradients that aren't just white and black. Before I go ahead here, I want to insert a note from after the fact of recording all of the original video and the experiments that I was doing, because at the time of recording, I did not appreciate a fact that is actually going to make this section a little bit more complicated, which is that depending on your display device and certain properties of it, the effects that I'm seeing and describing in this next part may or may not look the same to you. I'm going to start talking about things like how much of a particular gradient remains red looking or yellow looking or green looking, whether certain things look too desaturated, too bright, too dark, and so on. And to a certain extent, you'll be able to see the effect I'm talking about in some cases, no matter what, but in a lot of cases, the effect will depend on whether or not your monitor or display device recreates the image in the same way that mine was doing when I was first looking at it. And there's nothing I can do to make sure that you're seeing what I was seeing, because the display device you're using, I can't query it from within a video file and adjust to it or do anything like that. I'm showing you a raw bitmap that was captured from my screen at the time that I was looking at it, but faithfully reproducing. So here I am setting up those gradients, and if we zoom ahead to when I actually have them, what we can see is that it is kind of clear that, for instance, this gradient from red to green gets a little bit darker in the middle than it should when I'm blending in the sRGB space. But I keep toying with the colors here and playing with it for a while, and it's not as clean cut a win as I thought to switch to linear color blending. It seems like sometimes it works better in the linear space and sometimes works better in the sRGB space. For instance, one experiment I ran is to do a bunch of gradients that were primaries on one end and secondaries on the other. A secondary color in this case is one that is, for instance, yellow. It's fully red and fully green, so it's got two channels turned all the way up and one channel turned all the way down. So when I blend from a primary to a secondary, they all look kind of better in the sRGB blending case, and I think that that's for the same reason that the white to black looks better in the sRGB blending case, because now what we basically have is one channel is stuck on. For instance, if we're blending from red to yellow, then the green channel is stuck on, and the red channel is decreasing across the screen. And again, just like with the white to black case, if I decrease it across the screen in sRGB space, then it becomes perceptually linear. Whereas if I'm in the linear space, the red channel seems to get eaten up within the first 1/4 to 1/3 of the gradient, and the rest of it's just all yellow. Furthermore, when I'm blending from one secondary to another secondary color, it seems like it works better in the sRGB case and gets all blown out and close to white, a little bit too bright, maybe a little bit too desaturated in the linear color space. So it's not clear that gradients actually work out better no matter which color space you use. Maybe what's going on here is that I'm approximating something like the ideas of brightness and the rate of change of hue using an RGB color space, when I should really be going to a color space that isn't even following those three axes in any way, like an HSV, for instance. But chasing something like that down right now would be a little bit too far off topic. Instead, I'd like to take a look at another case of blending, this time not blending over space, creating a gradient, but blending one color on top of another using an alpha blend. That might be the sort of use case where it really does turn out looking better if you're doing all your blends in linear color space. So let's take a look at that real quick. If we skip ahead here, we can see where I've got the full test set up and running. So the way I ended up composing this test is there's a completely white rectangle with 3 stripes on it, a fully red, a fully green, and a fully blue rectangle. So there's no alpha blending happening there. Then I have a set of 3 vertical stripes that are red, green, and blue, and they have an alpha of 0.5. And then I have another set of 3 vertical stripes, again red, green, and blue, and those have an alpha of 0.75. And I'm using the standard alpha blending here, so the source color gets multiplied by the source alpha, and the destination color gets multiplied by 1 minus the source alpha. In this particular case, I can pretty definitively say I like alpha blending better when it's done in the linear color space. The transparent colors look a little less like they're randomly darkened out when I have, for instance, red and green blended together. And when something is blending over white, I like how it looks a little bit brighter. It seems to me like it makes more sense that way. Blending the red over the white in the nonlinear color space sort of darkens it quite a bit. What I can't really say for sure is that this is definitely more correct in any useful sense of the word. It definitely is my aesthetic preference that I would do alpha blending this way for transparent shapes, but I can't say that this is correct. It's just sort of different. If you like the darker look of the blends, then I'm not sure why you would actually do any linear color space. Which leads me to kind of a final thought here on these first 3 chapters looking at the sRGB linear conversions, which is that at least in the case of 2D graphics for things like a UI, but also for things like a 2D game, I'm starting to have a harder and harder time thinking of a benefit to using an sRGB linear conversion at all. That might be controversial, and so there might be some folks who really want to explain to me why I should care, but I've just looked at all the best arguments on this particular web page, which is the page that comes up when I look for the most detailed explanation I can of why it's important to get this right, and none of them actually seem to me like they're quote-unquote correct in any way that I can understand. They're at best aesthetically better. In some cases, they're definitely better, in my opinion, in the alpha blending in the linear case, but even that, I think, is not that clear cut. It's not like entirely busted the other way. So what exactly is the argument for why this is needed in 2D graphics at all? And keeping that in mind, what's the argument for why it's needed for anti-aliasing to be right? I'm not sure, but next we'll move on and take a look at that half of the problem. Chapter 4, Digging Deep on Anti-Aliasing. As I was trying to learn about this, the problem I kept running into is that any search about anti-aliasing will inevitably just bring up a bunch of forum posts, blog posts, articles, videos, and so on, talking about different methods of anti-aliasing and giving a medium to lightweight introduction to how to implement such anti-aliasing schemes in some cases, and in other cases just saying the graphics card does it. Yay, magic. Eventually, I found this video from Justin Solomon's Introduction to Computer Graphics course. This video really did fit the bill for me. It went deep into the theory stuff and also connected that to practice. It showed a number of useful techniques that I would actually need to know about in order to start implementing anti-aliasing, but also gave me the tools to think about how to tweak them for the kinds of things I'm experimenting with here in this video. There's not much point in me recapping too much of what's in that video because that video is already an excellent introduction to it, but it is pretty long. So I'm going to give you cliff notes, but I highly recommend that if you really want to get the theoretical baseline for thinking about anti-aliasing clearly, that you go and watch this video. For what I'm working on in this video, I'll just need to go over a few key points. 1. In theory, we want to think of an image, before it's been sampled, as a piecewise continuous color function that has a real number coordinate space. 2. The theoretically ideal anti-aliasing method involves applying a convolution. A convolution is a way of multiplying two functions together by sliding one function over the other and multiplying them across their entire range and creating a new value at each point that way. The function that defines the image is one of the functions we want to convolve. The other is a filter function. And when we convolve those, we can take samples from the newly created function to pick final sample value results. 3. Given the right conditions for the original image function and the sampling rate, which means how densely our pixels are packed over that function, the theoretically ideal filter function is some scaled version of a function called sync. If we had those conditions met and we used the correct version of the sync function, we could, in theory, exactly recreate the continuous image that we originally had. Number 4. In practice, approximations of the filter function sync have to be used. The unibox is one such crude approximation, and filtering this way is sometimes called a uniform filter or a box filter. It has problems that can be improved with other solutions like a Gaussian filter, but the box filter is commonly used because it works pretty well and it's very easy to implement. 5. An easy way to express the value of a pixel when we are using a box filter is as an integral over the area of the box centered at a pixel coordinate, and that integral integrates the piecewise continuous color function. What this amounts to is that thinking of anti-aliasing a geometric shape such as a circle or a line as computing the area of a pixel that is covered by the shape is not actually theoretically ideal, but it is considered a good method in practice. There are some ways that even in practice, this could turn out to not be good enough. And to know when those might come up and what you could do instead, you would want to learn more about the way the theory relates to practice. And there's a lot more to learn about this topic too. And again, I can't emphasize enough that if you really want to know this stuff better, you should go and watch this video. Now, my purpose here is to figure out if anti-aliasing should be blended in the linear color space or the sRGB color space. Unfortunately, the video did not touch on that subject, but it did give me the building blocks that I will need to evaluate that question myself. In common approaches to anti-aliasing, what you would do is some form of oversampling. In oversampling, you take more samples than you have pixels, and you assign those samples to pixels and mix them together somehow, probably approximating something like a box filter, but possibly something else too. The more samples you have per pixel, the higher quality the anti-aliasing results will be. So if you wanted to maximize the quality of your anti-aliasing, you would want to let the number of samples per pixel go towards infinity. And while we can't physically do that, we can sort of analytically do that by switching the problem up a little bit. In an analytical anti-aliasing approach, what we do is we pretend like there's an infinitely dense number of sample points, or nearly infinitely dense number of sample points, and we are trying to calculate how many sample points are covered by a shape without actually looking at every single sample point in isolation. In other words, the way we do this is by taking the area of a pixel that is covered by a given shape. If our shapes had only solid colors, so no gradients or other continuous functions defining the colors, and we were able to get infinitely precise area calculations for each shape in a pixel, what we would end up with would be a list of the areas of the shapes that partially cover the pixel and the color that is paired with each of those partial areas. The sum of all the partial areas would be exactly 1 because together they cover the entire pixel. And then by taking a linear combination of those colors and their respective weights, we would get the final value for the pixel. In practice, we can't spare the computation that it would take to figure out how much of a pixel is covered by each shape that might overlap it as we are rendering. So we have to do something a little bit simpler. And what we're going to do is compare and contrast the way the theoretical thing should behave for this shape-based approach to anti-aliasing to the way the practical thing has to work. And that will give us a way to tease out whether or not this sRGB style blending could ever work. So the way this has to work in practice is that we have a back buffer, and you can imagine that originally has a background color, and that then when a shape gets rendered to it, we calculate the area of the shape that covers that pixel, and then we blend the color of the shape with the color of the background, and we weight the color of the shape based on the area that is covering the pixel, and so whatever's left over is the color that was in the background. What we're going to see is that this does not compute exactly the same thing as the fully theoretical breakdown of the pixel into all of the subshapes that cover it, and then turn that into an issue for the sRGB blending. So let's start with this. If you have completely solid colors, so no transparency in the mix, and no shapes ever overlap each other, so you just have a solid background color and solid non-overlapping shapes, then this can technically get pretty close to perfectly approximating the value you would get from that integral. Of course, that is a lot of limitations, and we probably don't want to stick to just those limitations, so let's see how the approximation becomes more approximate and less exact as we add in more possible combinations of features. Let's start by looking at just what happens when we still use only solid shapes, but we start allowing them to overlap with each other. In that case, it's possible to have a case like this. I have a fully black pixel, and then I render a shape that covers, let's say, the right side of that pixel with white. And then later I have another shape that covers, let's say, the bottom half of that pixel with blue. The final areas of each color that make up this pixel are 1/4 black, 1/4 white, and 1/2 blue. So the ideal color for this pixel, as determined by a box filter, would be one that you get by taking the linear combination of black, white, and blue with those proportions. If we look at what happens in the same scenario using the accumulation buffer technique, what I have is a fully black pixel, and then half of that pixel gets colored white. So I blend first black and white 50% each, and I get a new color there. And then later I get half that pixel again covered by blue, and so I blend that, what I already had, which was half black and half white, with half blue, leading to a quarter black, a quarter white, and a half blue. So in this scenario, it exactly recreates the ideal value for the pixel according to a box filter. But with a very simple tweak, we can also make an example that breaks the accumulation buffer technique. Imagine again I have a black pixel, and then the right half of that pixel gets covered in white. Then after that, the right half of the pixel gets covered in blue. Now my final pixel is 1/2 black and 1/2 blue, and there's no white. But from the perspective of an accumulation buffer that is using alpha to blend in each step of the way, I'm going to end up getting 1/4 black, 1/4 white, and a half blue. Now let's turn to look at what happens if we start mixing in transparent shapes instead of only fully opaque solid colored shapes. The basic idea for creating transparent colors is to take any 3-component color and equip it with a 4th component that controls the degree to which the new color being rendered into the buffer will be blended with the color that was already present in the back buffer. The way that this creates an interesting problem is that alpha blend that you would use to create a transparent color is the same alpha blend you're using when you do analytic anti-aliasing to cover portions of a pixel in the accumulation buffer. So that means we need to answer the question, what happens when a pixel is partially covered by a partially transparent color? Let's imagine we have a black pixel again, and then a white shape is drawn with half transparency, so an alpha of 0.5, and that shape half covers the black pixel. Analytically, what we have is a pixel which is half black and half medium gray. So according to a box filter, the ideal final color for this pixel would be the color that you get when you take 1/2 black plus 1/2 medium gray. Now the issue that comes up from that is that this means blending colors into the background color twice. The first time to figure out what the blended color is given the transparency, and the second time to figure out what the color is given the partial coverage of the pixel. Both times I'm blending to the background color, and the reason that creates an issue is that in most graphics pipelines you only get one opportunity to do a color blend with whatever's in the back buffer. Now there is a way to make this work if both blends are using the same color space to encode the colors. For instance, if they're both in the linear color space. Take for instance this example that I was looking at a moment ago. If I have a black pixel and half of it gets covered in 50% transparent white, then what I can do is, first of all, I'm going to blend to black once by 50%, and that's going to give me the equation half black plus half white. And then I'm going to plug that into a second blend, which is going to go half black plus half of half black plus half white. That occurrence of black in both parts is no accident. That's the background color appearing twice. And since they're guaranteed to always be the same background color, it's not just necessarily going to be black, but it's always going to be the same, then I can rearrange this into 3/4 the background color plus 1/4 the foreground color. And to generalize the idea even further, it turns out if I have a transparent color and I know that it covers a portion of the pixel, I can just sort of multiply the transparency by the partial coverage value, and what I get is a new value, which is whatever I would get when I apply both blends. And again, the whole reason that I'm going over all of this is to emphasize that all of this is true and works correctly, but only so long as you do both of them in the same color space. So if it turns out, for instance, that I like using linear color space for my alpha blending to make transparent colors, but then I want to use sRGB color blending for some reason because I think it looks better for anti-aliasing, then combining these is no longer so easy. And since I do, in fact, kind of prefer linear color space for the alpha blending to create transparent colors, that gives me my first reason to think that I should try to do anti-aliasing with blending in the linear space. Now, based on all of that, there is another direction you might want to consider going, and I'm going to explore it a little bit and ultimately show why it doesn't make a lot of sense to go this direction. So the idea might be to say, hey, if anti-aliasing turns out to look better in an sRGB type of blend, why not account for that when you're combining the alphas? So you'll have your transparency alpha, and then you'll compute the pixel coverage, and you'll just put it through one of those power curves, maybe x to the 2.2 or x to the 1 over 2.2, whichever one turns out to be the right one, and then multiply those together. That way the pixel coverage can be an alpha modulated by the sRGB curve, and the transparency can be an alpha that is going along the linear curve. The issue with this will be a little easier to see if we back up and think through, again, from first principles, how we're trying to approximate the box filter by doing this accumulation buffer approach. Let's say I had a pixel that was split up into 3 equal colors, and those colors were all fairly close to white, maybe being a little bit less red, a little bit less green, and a little bit less blue in each case. Whatever I do with the blend factors, it's important that all 3 of them add up to 1. For instance, if I said originally they would be 1/3 each, but then I wanted to put them through this power curve that takes 1/3 to 0.0892, then the final result is going to end up being too dark. I had 3 colors that were mostly white, and so the final color should be mostly white, but I did this strange modulation on all of the blend factors, and so the sum on those blend factors was less than 1, and I end up with a color that even after I convert linear back to sRGB is much darker than nearly white. Now, this isn't directly going to become a problem, it's just a theoretical issue. The real problem is going to be if I start doing something like, say, putting the coverage of the pixel through a curve like that before I send it to the blend unit, then I'm going to still end up getting a sum of 1 on the weights. The weight for the new color will be whatever the modulated alpha was, and the weight for the color that was already in the accumulation buffer will be 1 minus that amount. But this is strange for a new reason. Although it's made the blend weights always add up to 1, now the back buffer color is getting a much heavier weighting just because it's the back buffer, even though from the theory point of view, it's the same amount of pixel coverage whether I consider one color the back buffer or the other. To put it another way, look at this pixel which is half white and half black. If I consider black the background color, then when I go to blend this, what'll happen is I'll take the 50% for the white and modulate it down by the curve. But if I consider white the back buffer, then when I render black on it, I'll take the 50% for the black and modulate it down. Even if it's the exact same pixel in terms of the theory here, where they should each get a 50% weight, what I'm doing is essentially weighting it towards the background by doing this idea of converting a linear alpha to an sRGB alpha. So where I've ended up is that for practical purposes, I need to use a back buffer technique for doing my anti-aliasing and combining each shape as I go. And I need to use a single blend step to compute the blend for transparency and the blend for anti-aliasing at the same time. So I probably want them to both be the same. And I probably want the transparency blending to be linear. So I probably want them both to be linear. And the only idea I had to maybe sneak around that was to modulate the anti-aliasing before I combine it in, but we've just seen that anything I do to modulate the anti-aliasing leads to a bunch of even worse problems. That pretty thoroughly covers all the theoretical ground for why I think I have to do my anti-aliasing blend in linear space. But now what we're going to do is go and do some actual rendering experiments and see what the results look like to find out what happens in practice. Chapter 5, Anti-Aliasing Experiments. The first experiment I want to do is to look at the anti-aliasing for simple unrounded rectangles. In particular, I want to look at rectangles of a relatively thin width so that we can see if they look about the same width when they are spaced out at different sub-pixel positions. And I want to compare the quality of the pixel coverage anti-aliasing when it is blended in sRGB versus when it is blended in linear. Hopefully what this will do is give me a good idea of just the base case, the simplest possible, most important part of the anti-aliasing, and how it turns out given various blending spaces. Alright, if I skip ahead to where that test is done, we can see here I've got on the left side a series of rectangles. They're each 2 pixels wide, and they're spaced out by 2 1/16 of a pixel between each other. So the gap between each rectangle is just a little bit more than 2 pixels. And then on the right, I've sent down the exact same geometry, obviously shifted over to the right side of the screen, but the layout is the same. And at least to my eye, it seems very clear that the rectangles on the left all look like a pretty good approximation of rectangles of the same width, and the ones on the right do not. They all look wider, except for the very first and last ones, the ones that almost line up on the grid. Those look thin, like a 2 pixel wide rectangle, but as soon as it gets to about 1/8 or more of a pixel covered, that extra pixel gets so bright that it looks like 3 pixel wide rectangles, and the gaps look like 1 pixel wide gaps. And this is the part where I start getting really concerned, because this is the simplest possible case. I can't really imagine that the anti-aliasing for pixel coverage that I'm doing here is wrong, but it's definitely causing the rectangles to appear to be different width. And these aren't even animating yet. These are just sitting still on the grid. And when I blend my anti-aliasing with linear colors, those partially covered pixels get so bright so fast that it doesn't look like the rectangles are the same width and maybe a little bit fuzzy because they're unaligned. It looks like a wider rectangle. But this might not by itself be convincing. Maybe rectangles are some kind of a special case because they're so aligned to the pixel grid or something. Maybe this kind of anti-aliasing does look good for the kinds of cases where anti-aliasing works well, which is on making diagonals or curves look better, and maybe it just doesn't work super well for cases like trying to make the illusion of a rectangle sitting in between pixels. So if that's the case, we should be able to compare 2 shapes that aren't perfect rectangles, and I think the easiest case is to use circles. Previously in my video series, I made an analytical circle anti-aliaser that worked by classifying the intersection with the pixel in several different cases, and then calculating the area based on which case it's in with a very small amount of approximation. But something that's hard about that method is it's really difficult to verify that I actually wrote it all correctly. It did give really good looking results, especially when I was using sRGB blending, but maybe that means it's actually wrong. Maybe the reason it looks bad is because the circle calculation isn't quite right. And so then the question becomes, is there some way to write a pretty accurate circle area without having to worry about whether or not it's correct? And I think there is a technique to do it. It's not the technique you would use to render it for speed purposes, but when what we want is a really high confidence that we correctly calculated the area of a pixel that's covered by a circle, I think that the way to do it is going to be to do all the calculation on the CPU using a highly analytical method, which is going to be calculating the area under an integral. Now, I got this idea from someone on GitHub who was doing the same kind of thing, trying to make a very smoothly anti-aliased circle. I'm not going off of their code too much, but it's the same basic idea what I'm about to do next. The nice thing about this method is it pretty much eliminates all concerns that my approximation might be too sloppy, and it gives me a pretty good way to verify that my results are correct because I can apply it to circles arbitrarily small, and so I can look at a series of circles getting bigger and bigger and calculate the entire area that is supposedly within that circle according to the area contributed by each pixel, and that'll give me a couple of ways to verify that the results coming out look correct. Now, if I was practicing my integrals a lot recently, I probably could take the time to work this out, but I'm just going to go find an indefinite integral calculator online, and so plugging that in here, it gives me this result. If I have a formula for the indefinite integral that is accurate, then I can evaluate that twice on two endpoints and calculate the area under the curve. And later on, it's also going to be convenient to flip that around and calculate the area under the curve sort of sliced in the y direction instead of in the x direction. And that's going to work just fine given the symmetry of x and y in the formula for a circle. Once I've plugged that formula into my code here, I run a quick sanity test to make sure that when I give it two endpoints to calculate the area of an entire semicircle, because this is only calculating the area under the circle's top half, but when I plug that in to check it, I should be able to compare it to the formula for the area of a semicircle, which is 1/2 pi r squared, and confirm that it does indeed look like it's getting the correct results. Next, what I need to do is a bit tricky. I need to build a system that'll walk across a grid of unit squares and determine the area of the intersection between the unit square and the circle I'm trying to render into the buffer. And as I work on it, I kind of end up using the same set of cases that I did for the approximate circle coverage that I did previously in the video series. The big difference is once I figure out what case I'm in, the way I calculate the area is going to be perfectly precise, or as perfectly precise as floating points will allow me to get. So I'm not going to just get some endpoints and grab a triangle or a couple of rectangles and figure out the area approximately. I'm going to try to figure out the area by figuring out intersection points with the edges of the unit square. Depending on which case I'm in and where those intersection points are, I can chop up a pixel into different portions of what area of that pixel are covered, and then do a couple calculations. The integral gives me the area under the entire curve. I can subtract out all of the extra area that's counting from pixels underneath the one I'm actually filling in, like as shaded in this diagram here. And sometimes I'll have a case or two where there's some other extra stuff I want to add in. So I kind of go through, figure that out, and then run a separate set of sanity tests on that idea. In these sanity tests, what I'm doing is walking the entire grid of unit squares by some circle that I want to test and summing together all of the areas. So I'm getting area from each unit square. Some of them have a unit area of 1, some of them have a unit area of 0, and some of them have a unit area that is sort of fractional. And I'm adding all of them up and seeing how close that is to the area that I get from the area of a circle formula. And if they're a pretty close match, then I can be pretty confident that this whole system is working correctly. So after a little more bug fixing and looking through those cases to make sure they all make sense, I do start getting results that pass the sanity test. And finally, I move on to using this idea, the ability to get the area covered by a circle in a unit square. and plug it into a pass that will generate an anti-aliased buffer that contains a circle. Now I'm doing all of this on the CPU instead of in a shader just so that I can do these sanity tests and write the more complex code that gets a very accurate result without having to think super hard. In the version I did before, it was a little bit more shader friendly, not by that much, but a little bit more. But in exchange for being more shader friendly, it was harder for me to do anything to verify the results with those sanity tests, and it was a little less accurate. So the trade-off now is I've done all the computation on the CPU, I gotta fill a buffer and submit it, which I'm gonna do through a texture. And here we can see the results. So on the left, I have my circles. I've got a radius of 5 circle, a radius of 25 circle, and a radius of 125 circle. And on the right, I have the same radiuses. These are the same textures. The only difference is, of course, on the right, it's undergoing a linear to sRGB conversion afterwards. Now, again, to my eye, these circles on the right-hand side just don't look as good. The smallest one looks like it's been blown up a little bit. It looks a little bit more like an octagon than a circle. The other two look a little bit like they have flat edges. If you look here at the top and bottom, left and right, there's a section there that looks a little bit more flat than it should be. And this isn't because the texture ran out of space or because the geometry is off or something. The textures have a good amount of extra padding. I added 5 or 10 extra pixels on top, bottom, left, and right of each of these. So there's enough room in the texture to capture all of the detail. And there's definitely enough room in the geometry I'm submitting and all that. So that's just what the anti-aliasing itself produces. Furthermore, and I don't know if this comes through in a YouTube video, but if you run the demo yourself, I'm sure you'll see it. There's sort of jaggedy, pixely looking artifacts here, a little bit closer to the edge, but not quite on the flat part of the edge. And so to me, this looks like poorly anti-aliased geometry, right? This looks like it's wrong. And the one on the left that is not undergoing a linear to sRGB conversion looks right. In a lot of cases, it's been useful to just think about this sRGB versus linear color space conversion problem in terms of what it does to the brightness of the pixels that come out. But thinking about it that way really only makes sense when I'm talking about rendering white on a black background or black on a white background. What happens if I'm not just using a white on black anti-aliasing, but I'm trying to blend a colored shape onto another colored shape? That's where it starts to get tricky, because if I'm using linear color blending there, that's going to give me that kind of linear color blending that I like for the purposes of transparency. But if I'm using sRGB color blending, that's going to give me the kind of color blending I like for anti-aliasing a white circle on a black background. And this is where I'm getting confused, because it's not just a matter of the theory mismatching what I'm seeing. It's also that I can't seem to find one single path that consistently solves all of these problems, which I find very surprising. So for my final experiment, let's try the same thing again, but instead of white on black, we're going to have a colored background and a colored foreground shape, and see what happens when we use the color blends in sRGB space and in linear space, and we blend by the amount given by the texture. So one thing I have to be careful about thinking through here is, again, remember, I'm going to send a color down that's not going through a texture sampler, which means that if I send down a color to the non-sRGB correction side and then the same color to the sRGB correction side, I might get a color artifact just from the fact that I'm actually not doing the convert from sRGB to linear on the right-hand side that I need to do. But I'm going to actually end up sidestepping that issue in the way I set this experiment up by just only applying this experiment to colors that have 1s and 0s in their RGB channels. The values 1 and 0 convert to themselves given the sRGB to linear conversion functions. They're the fixed points, right? So I don't need to do conversions unless I start using numbers between 0 and 1, and that way I can just get away with writing one new shader. What this one shader does is look at a texture and sample from it, but instead of using that as a color, it uses just the R channel, the red channel, as an alpha value or a coverage value, and then it takes a uniform color and sends out the final fragment to be the uniform color modulated by the alpha from the alpha taken from the texture. And looking at this final result, I'm once again having to conclude that I actually like it better when the sRGB blending is being done. The linear color blending is causing the circles to look all aliased in almost every case here. And in the case of red on green and green on red, I'm even seeing the impression of yellow pixels around the edges. So I just don't see how this could ever be the ideal way for me to do anti-aliasing. There's now two different experiments. It causes a huge problem with the rectangles, and it's causing all these problems with softer curves like on a circle. So it seems like there's something just fundamentally wrong about claiming that the theory is that you blend anti-aliasing in the linear color space, right? That's the only thing I can conclude from this. At the very least, 2D graphics don't look better when I do this. Whatever theory you've got about it, this is not the right way to do it. And I can only conclude from all of this that probably the theory is wrong. However, before I make that final conclusion, there is one last thing that I'd like to spend some time on in this video. Chapter 6. Dealing with some possible explanations for the issues I'm having. I've gone through all my experiments and my best explanation of the theory behind them, and so far I haven't seen it all clicking together and making sense. But there is a category of explanation that I haven't dealt with yet, and that is explanations for things outside of the main theory. So the main theory is, the color space conversions and how those are supposed to work and why it makes sense to do them, the anti-aliasing techniques and why it makes sense to do them. But outside of that, there are some other things that you can get wrong that basically lead to the experiment not giving the intended result, but aren't really addressed by the theory itself. They're just facts about the setup. They're additional details, free variables, things that can easily go ignored, but that are actually relevant. So I want to make sure to take those kinds of explanations seriously before I make any final conclusions. First, the most fundamental suggestion that I find a lot is that it's possible that my monitor is not calibrated correctly. Now, if this was true, it would probably mean that other people who are looking at the same thing I'm looking at, but on different monitors, are going to see things slightly differently, and the people who are agreeing that it looks wrong, their monitors must also all be calibrated incorrectly, which raises the concern that maybe incorrectly calibrated monitors are the norm, which would mean that even if I got all of the rest of this right, I would still end up with some people getting the wrong results without knowing why, which is a little bit concerning. And I don't really know what to do about that. But setting aside concerns like that, let me play the game according to this claim that if my monitor was calibrated correctly, then I would see these results better. So what is the idea behind correctly calibrating your monitor? Well, the entire model of color spaces that I've been running with has assumed that the system sends sRGB colors to the monitor, and the monitor interprets those and reproduces colors in its pixels from those sRGB values. If the monitor can be miscalibrated, that implies that it might be making some pixels too bright and some pixels too dark, by interpreting the values that it's given by the software into actual colors in the pixels in some way that doesn't match the expectation from sRGB. Now, the question becomes, how could I test if that's happening first? And if it is happening, is there any way at all to do something about it second? To deal with the first part, there is a pretty common way to test this. So the idea is to create an image that is made out of a mixture of some blocks that are full solid grays and other blocks that are stripes or polka dots or checkerboards or something. And the idea is that the polka dots or stripes or checkerboards are pure white and black. Those can't be miscalibrated because whatever curve we're using, they're going to have 1 is always going to be the largest possible value and 0 is always going to be the smallest possible value. And so our brightest and darkest values from the monitor will be matched to the 1s and 0s. It's the values in between that require some kind of calibration curve. So the idea is to use pure white and pure black pixels in some kind of tightly enmeshed pattern like a checkerboard or stripes to create the effect of another level of energy coming from the screen, and then use something like squinting our eyes to blur out the difference. So for instance, if I create a block that is a perfect white and black checkerboard, and then I squint, I should be getting half the amount of photons or half the amount of energy coming to my eye as I would have gotten if all of the pixels were pure white. Of course, this does sort of incorrectly assume that black is going to be pure black and have 0 photons coming from it, which won't technically be true, but it's a good model for building this kind of testing experiment thing that we're trying to do to calibrate the monitor. Then what I can do is render several of these blocks next to each other. One of them can use a 50% gray value in the sRGB space. Another block can use the 50% gray value in the linear space that then gets converted to sRGB on its way to the screen. And the third block can be this checkerboard that's 50% pure white and 50% pure black. Then, if my ability to squint does blur it out correctly, that block should look the same or very similar to the 50% linear color value, the color value that has 50% the energy brightness, and it should not look the same as the block that has 50% sRGB or perceptual brightness. So I think the easiest way to do that is just going to be to throw a texture into the non-color corrected part so that I can just make a bitmap and send it straight to the screen using my test program. And that way it'll be baked right in and I can do my squint and see if my monitor seems calibrated or not. So let's give that a try. So after coding this up and taking a look at it, initially it seems pretty strongly to me like the checkerboards are too dark. They look not quite as dark as the darker solid color rectangle, but very close to that. Definitely those checkerboards look closer to the dark rectangle than they do to the bright rectangle. And that's wrong because the checkerboards are simulating 50% energy, the average between a white pixel and a black pixel. And that's supposed to match the appearance of the linear color brightness, 50%, and not the darker value, which is the sRGB 50%, which means maybe my monitor is uncalibrated. And so I go and do a little looking around on how to do that. And it turns out I have to mess with my settings a little bit. I have some monitors tied together because I've got a drawing tablet and a main monitor that I want to have together, but I can't calibrate monitors. The Windows color calibration thing won't let me calibrate monitors while I have duplicated monitors, so I have to unplug some stuff and move stuff around. But you can see here I'm running the color calibration, and I do make some tweaks to the settings in Windows to calibrate the gamma a little differently. And when I go back and look at this program again with the newly calibrated monitor, it turns out that all of the things I've been seeing as problems are fixed. And in fact, now it's the little rectangles that are supposed to be the same width. They all look the same width on the linear side. And on the sRGB side, those rectangles look like they get too dim. They look too small. And the circle looks a lot smoother on the linear color side. And now I see the jagged edges of a pixel aliasing problem emerging on the sRGB side. And in fact, even the color warping of the color on color blends is gone in the linear side and appearing now in the sRGB side. So, I mean, I think that kind of settles it. I mean, this really blows my mind. Even the color to color gradients look better now. They look more like a perceptually linear gradient. I suppose the one thing that didn't change here is that white to black gradient that was the original point on which I focused. That white to black gradient still looks somewhat nonlinear in the perceptual gradient sense, in the perceptually linear sense. It looks a little nonlinear on the right-hand side, but that's always the way it's supposed to. And it definitely looks less exaggerated now. It looked very exaggerated, the nonlinearity before. And while it's still there, it's not so much that it actually looks like you could tell for sure that it's a wrong gradient, which it sort of looked like that before. So I think that's pretty awesome. I had no idea that color calibration could make that major of a difference. I didn't think it would, for instance, fix the anti-aliasing on one side and break it on the other side of the monitor if I went and calibrated the monitor. I just figured even if my monitor was uncalibrated, it couldn't be that big of a deal. But I've learned better now, and so I guess that'll be the message of this video. After all of this experimenting and studying the theory as precisely as I could, the variable I didn't have right was that I was not actually getting the sRGB effect from the monitor that I was supposed to. I was sending sRGBs to the monitor, and it was not interpreting them in quite the right way. However it was calibrated was off, and so I was getting things that appeared wrong, even though all the data flowing through was right and I was applying the theory right. The final appearance was wrong because of this other variable. The monitor itself can be wrong if you don't calibrate it. And that's really good to know. So hopefully other people can take that away from this. If you're going to do graphics work, probably calibrate your monitor carefully first. And if you're having things look aliased, maybe calibrate your monitor before you complain about it. On the other hand, it is still kind of going to be an issue forever if I and plenty of other people that I talk to have their monitors uncalibrated and don't know how to do it because it's, buried in the operating system, not obvious that this is something you should pay attention to. It's always going to be the case that some users are going to have a poorly calibrated monitor. And so if that can affect the aliasing, it's always going to show up for somebody. But at least now I've got myself in a spot where the theory of this stuff and the practice of it are lining up, which is pretty important to me. I made all of these experiments and the final calibration test thing entirely in a standalone program. So if you want to see what your monitor looks like when you compare sRGB style blending with more correct linear color blending and a linear to sRGB conversion, and if you want to see if your monitor is calibrated, you can download this program source code and build it for yourself if you're on Windows. The link to the repo for that code will be in the description. For now, I think that is way more than enough for today. This has actually been quite a long project, so it's kind of interrupted my plans for the rest of these graphics videos. But for now, I need to take a break from making videos and go calibrate all my monitors. See you next time.